Assalamualaikum, my name is Aiman Amri bin Mokmin and I will be presenting on the distillation column design and emergency response plan together with Highlight for today's presentation.
Assalamualaikum and good day. My name is Putra Najmin Farid bin Abdul Razak and today I will be presenting the process control system part and also the design equipment of vessel separator V104.
Assalamualaikum. My name is Nordiana Andrus Pakana. I will be presenting on the process heat integration and reactor R101 design.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adila Amira binti Ayub and I will present the reactor design and economy analysis.
Assalamualaikum and very good morning to everyone. My name is Muhammad Harib Zulkifli. I will cover on introduction and a little bit on equipment design, specifically on heat exchanger. Our plant design aims to produce 9,000 tons of ethanol annually. We plan to synthesize the ethanol via dimethyl ether production from hydrogen and carbon dioxide with operating temperature ranging from 25 to 410 degrees Celsius and pressure between 1 to 40 atm. The equipment used throughout the process includes 2 reactors, 1 distillation column, and 3 separating vessels. The final product is estimated to be 99% purity of ethanol. As for today, we will be presenting on heat integration, process control system and instrumentation, equipment design, economic analysis, and finally, plant safety and layout.
Assalamualaikum. So for process integration, in this process there are 3 streams that is analyzed, which are stream number 3, the cold stream, stream number 5, the hot streams, and stream number 14, also the hot streams. So as shown in the slide, the cascade done, heat cascade only done once due to positive values of cascade. Hence, the pinch point is 405 degrees Celsius. Above pinch point is 410 degrees Celsius, while below pinch point is 400 degrees Celsius. Hence, from what we can see in the cascade done, the minimum heating requirement QH min is 0 kilowatt, while minimum cooling requirement is 805.87 kilowatt. Here, there is a threshold happen. So in this process, threshold problem occurs as only cold utility is available, while the hot we have 0 kilowatt. In the next slide, it is shown that the heat exchanger network HEN of the process. So we can see that cooler is needed. There are balance of cooler for cold utilities at H1 and H2. So if combined, the value is 805.94 kilowatt. Hence, in the next slide, the number of heat exchanger required only 2 to compare with before integration, which are 3, 2 heater and 1 cooler. But in the next, after the integration, the process only needed 2 cooler. So finally, after doing the pinch analysis, the energy utility saved can be up to 65%, and the cost utility saved is up to 80%. Hence, these are the PFD of the before integration and after integration. So after integration, the heat exchanger is reduced to only 2 equipment. Thank you.
Okay, now I will explain the process control system that we use in our main equipment. There are 3 types that we use, which is a feedback, feed forward, and also the cascade control system. Most of our process, we use cascade control system to regulate the temperature of the process. For fixed bed reactor R101, there are 3 main parameters that we're going to control. which is the pressure inside the reactor, the flow rate input of the reactor, and also the temperature inside the reactor. Feedback control was used for the flow rate, and the feed-forward was used to control the pressure. And the cascade control system will manipulate the cooling water to control the temperature inside the reactor. Next is for the heat exchanger. Here we also use a cascade control system whereby the temperature of the liquid at the stream 6 will be controlled by regulate the cooling water. And the outer loop is the temperature control, while the inside loop is the flow rate of the cooling water. The third is the reactor R102. This reactor also has the same control system with the R101 because they use the same reactor and also need to control the same parameter. Next is the vessel separator V104. Here we would like to control the flow input, the pressure inside the tank, and also the level inside the tank. Feed-forward control system was used to control the pressure, and the feedback control system was used to control the flow input and also the level of liquid inside the tank. Last but not least is distillation column 101. There are 4 parameters that we would like to control here. Cascade control system was used to control temperature by regulate the steam inside the tower. Apart from that, feedback control system was used to control the pressure, the level of liquid inside the tower, and also the level of liquid inside the reflux drum. All of this control was installed to prevent any overpressure and also overflowing inside the equipment.
Assalamualaikum. For reactor R101 design, I'm going to highlight on the process that's involved in the reactor and summarize the chemical and mechanical design of the reactor R101. So first of all, the chemical reactions that involve in the reactor is the reaction of dehydration of methanol into dimethyl ether. So the main product of the reactor is dimethyl ether. It is to synthesize DME. The overall reactions are exothermal process from carbon dioxide and oxygen. So the reactions catalyzed by copper oxide, zinc oxide, and aluminum oxide, where these catalysts are widely used in the chemical industry to produce methanol, with the composition of copper oxide 55 weight percent, zinc oxide 21 to 25 weight percent, and aluminum oxide 8 to 10%. There are 3 equations involved, which first one is the methanol synthesis, second equation is the water gas shift reaction, carbon dioxide plus hydrogen, and the third is methanol dehydration to produce dimethyl ether. So as we can see at the right side of the slide is the reactor parameter condition, where stream inlet number 4 with temperature of 232 degrees Celsius and pressure of 37 bar. The gas flow into the reactor is 5002.3 kg per hour, with the component composition are carbon dioxide 0.2053, hydrogen 0.0901, carbon monoxide 0.5197, and dimethyl ether DME 0.1117, and water 0.073. The outlet stream is stream number 5 with the temperature of 222 degrees Celsius, pressure of 440 bar, and gas flow of 2.57 kg per hour. So as what we can see here, we can conclude that the reaction is non-isothermal reaction. With the composition outlet, carbon dioxide 0.0365, hydrogen 0.0367, carbon monoxide 0.3103, DME 0.3722, and water 0.2443. Here we can see that the DME is produced more compared from the inlet stream. Here we can see the summary of chemical design, where the design tube, we needed 143 number of tubes for the reactor with the thickness of 2.6 millimeter. The arrangement of the tube arrangement is selected as equilateral triangular. Before I proceed, The reactor R101 is a fixed bed reactor, therefore the catalyst in the reactor is copper oxide, zinc oxide, aluminum oxide with weight of 732 kilogram and shape of spherical. The catalyst bed density is 1140 kilogram per meter cube. Also, the reactions in the reactor are exothermic, therefore heat releases. Hence, cooling jacket is needed. The type of cooling jacket is spiral baffle jacket with pitch of spiral of 200 millimeter, and the number of spiral needed in the reactor is 12. Next is the mechanical design. As what we can see in the slide, the design pressure of the the reactor is 4.07 Newton per millimeter squared, and design temperature is 255.2. For the body of reactor, material selected is stainless steel grade 316, and the type of head of the reactor is ellipsoidal head with the thickness of 12 millimeter. The wall thickness of the reactor is 23 millimeter after calculated with the stresses allowed. The total dead weight of the reactor is 140,245.7 Newton. So that is all for reactor R101 design from me. Thank you.
The heat exchanger is used to cool down process stream from 222 to 40 degrees Celsius. This is important to ensure the effectiveness of the separating vessels ahead. Assuming there is no heat loss to surrounding, a mass flow rate of 5,932.8 kg per hour of water is needed to handle the cooling process. The water inlet is 30 degrees Celsius while the outlet is 65 degrees Celsius at constant pressure. The type of heat exchanger design is shell and tube with arrangement of one shell pass and two tube passes. Because of economically friendly and yet has high durability, carbon steel is used as the material of construction. The number of tubes inside are 76 tubes with 16 mm outside diameter, 13.6 mm of inside diameter, and length of 3.048 meter, equivalent to 10 feet.
For reactor design, first of all, the process of the reactor is to produce ethanol. So for the ethanol synthesis, the reactor will accomplish in a dual bed reactor. So for the inlet of this reactor, the pressure and temperature is 15 bar and 90 Celsius. Follow with the outlet, which the temperature will be increased to 410 Celsius. For the material constructions of this reactor, we choose stainless steel because stainless steels have a high resistance of corrosion. In the presence of oxygen, stainless steel will develop a thin, hard adherence film with chromium oxide to protect metals from corrosion. For diameter and length of this reactor, length for this reactor is 7.029 meter and diameter for this reactor is 2.34 meter. Follow with the number of tube is 209 tube.
Okay, now I will proceed with the design equipment for separator V104. The separator is functioned to separate the syngas from the alcohol, which is the ethanol and methanol. Here is the schematic diagram of the separator. Design temperature is 5% more from the operating temperature, while the design pressure is 10% more from the operating for safety consideration. With the diameter of 5000 mm and height of 2000 mm, the separator uses ellipsoidal head, which is the most suitable in terms of its application and also its cost. Material used for the separator is carbon steel, which has a lower cost and also can withstand and has a good resistance for our material inside our process. Straight skirt also was used as a support for the separator. That's all for me, thank you.
As for the distillation column, the aim is to gain high purity ethanol at the bottom of the column. The operating pressure and temperature for this column will be at 33 bar and 64 degrees Celsius. All of the carbon monoxide and carbon dioxide that enter the column will be the top product of the column together with almost all of the methanol. The bottom product will be ethanol with 99% of purity. The column is set to be 44 meter height with 2 meter of diameter. To reach the high purity of ethanol, we will need 83 stages of tray. The material of construction for both tray and column will be carbon steel.
For economic analysis, first of all, the total cost for equipment is 10,918,781 ringgit 26 cent, include reactor, heat exchanger, separator, and distillations column. But for the total module and gas cost is 12,530,161 ringgit 80 cent and 17,839,552 ringgit 52 cent. The terms of grassroots refer to a complete new facility in which the construction is started on essentially undeveloped land, a grass field. For the term total module cost, refer to the cost of making small to moderate expansions or alterations to an existing facility. From the table, the fixed cost is 60,297,687 ringgit 52 cent. Fixed costs include from direct costs and indirect costs. For the manufacturing costs, the estimate the cost, it must consider the raw material, utilities, waste treatment, and operating labor. The total manufacturing cost will be 115,290,922 ringgit 60 cent. The revenue was calculated based on value of ethanol and methanol sold. From the calculations, the estimations for ethanol and methanol was fully sold out. So the total revenue for both is 171,365 ringgit. The annual profit is 59,853,637 ringgit 90 cent per year, and after the tax with 55%, it become 32,914,000 ringgit 89 cent. The payback period around 4.3 years, but this period can be changed due to the economic condition. Thank you.
Moving on to the Emergency Response Plan or ERP, generally we have divided the plan layout into two main areas. The first area is the area with the high hazardous working environment, such as the processing area, the chemical storage area, the waste treatment area, and the utilities area. This area covers two-thirds of the whole plan area from left to the middle of the plan layout. Mostly, the right side of the plan layout consists of places with less hazardous working environment, such as the cafe and the administration office. In this plan layout, we have prepared two assembly areas to make it easier for the staff to access the assembly point in case of any emergency. The front assembly point will be for those who work at the front area of the plant, and the back one is for those who work at the back side of the plant. The staff who works in the middle of the plant need to choose on which assembly point is easier for them to access. The next one is the hierarchy of the plant. As you know, chemical production plant has always been at risk and must be managed properly. Actually, there are many hazards at the production plant. However, due to time constraints, allow me to explain 5 major hazards that may occur at the plant. As you can see, the table shows some possible hazards that may occur at the plant. The first one is at the loading raw material activity. The hazard that may come from this activity is the vaporous chemicals like carbon monoxide, as carbon monoxide is at gas state at standard conditions and can cause cancer or even unconsciousness. So, to avoid this from happening, it is advisable to use appropriate PPE and elephant hose when unloading the raw material. The next hazard is the high temperature of the reactor zone, which can cause kiln burn or even explosion at the plant. The risk control that can be taken is to have a signage or barricade the zone and install the control system at the reactor. As for the third hazard, same as reactor, the high pressure of the separator can cause explosion at the plant, so it is crucial to install control system to avoid this from happening. The next potential hazard is the vaporized and flammable chemicals at the unloading product activity. This hazard can cause unconsciousness and fire, which can lead to explosions at the plant. It is advisable to use elephant hose and wear appropriate PPE when doing this job. The fifth hazard is the toxic water at the waste treatment. This toxic water can cause poisonous, and it is advisable to put signage and barricade also the area as the risk control measure. Thank you.